What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of improving the performance of large multimodal models, LMMs, by enabling them to learn from a large number of demonstrating examples in context without the need for model parameter updates. This method, known as many-shot in-context learning, ICL, allows LMMs to specialize to new tasks without additional model training. By drastically increasing the number of demonstrating examples, researchers aim to explore the impact of this approach on model performance across various datasets and image classification tasks. The goal is to demonstrate that providing LMMs with many demonstrating examples leads to substantial performance improvements compared to providing only a few examples, and to measure the data efficiency of the models under many-shot ICL. Additionally, the method of batching multiple queries into a single request is explored to achieve similar or better performance in a many-shot setting while reducing per-example latency and inference costs. Ultimately, the new method aims to enhance the adaptability and efficiency of state-of-the-art multimodal foundation models in handling a large number of demonstrating examples for improved performance on diverse tasks and datasets.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method of many-shot in-context learning, ICL, works by providing state-of-the-art multimodal foundation models, such as Gemini 1.5 Pro and GPT-4o, with a large number of demonstrating examples to improve performance on various image classification tasks. The method involves conducting experiments on 10 datasets spanning different domains and tasks to benchmark model performance. By scaling up the number of demonstrating examples by multiple orders of magnitude, the study shows substantial performance improvements compared to providing only a few demonstrating examples. The performance of Gemini 1.5 Pro generally improves log linearly as the number of demonstrating examples increases, while GPT-4o exhibits less stable improvements. The study also measures the data efficiency of the models under ICL as the number of demonstrating examples is increased, with Gemini 1.5 Pro demonstrating higher ICL data efficiency than GPT-4o on most datasets. Additionally, the method explores the impact of batching multiple queries into a single request, which can achieve similar or better performance than single query requests in a many-shot setting, while reducing per-example latency and inference cost. The study further investigates the benefits of batch querying in a zero-shot setting, attributing performance improvements to domain calibration, class calibration, and self-generated demonstrating examples due to autoregressive decoding. Overall, the proposed method of many-shot ICL aims to enhance model performance by providing a large number of demonstrating examples and optimizing query batching strategies to improve efficiency and cost-effectiveness in multimodal tasks.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the many-shot in-context learning ICL method with large multimodal models include substantial performance improvements without the need for model parameter updates, leading to enhanced specialization to new tasks without additional training. This method allows for scaling up the number of demonstrating examples by multiple orders of magnitude, resulting in significant performance enhancements across various datasets and image classification tasks. Many-shot ICL also demonstrates higher data efficiency, particularly with Gemini 1.5 Pro, compared to traditional few-shot ICL methods. Additionally, batching multiple queries into a single request reduces per-example latency and inference costs while maintaining or even improving performance, making the method more cost-effective and efficient. Many-shot ICL enables quick adaptation of large models to new tasks and domains, potentially eliminating the need for fine-tuning and facilitating the development of customized approaches. The method also shows promise in reducing biases and hallucinations in models when carefully curated demonstrating examples are used, which could have important implications for mitigating biases across different subgroups. Overall, Many-shot ICL with multimodal foundation models offers a practical and efficient way to improve model performance, adaptability, and cost-effectiveness in various applications.
How is the method validated or tested?
The method is validated or tested by conducting a large suite of experiments to benchmark the performance of two state-of-the-art multimodal foundation models, GPT-4o and Gemini 1.5 Pro, on 10 datasets spanning various vision domains and image classification tasks. The experiments involve scaling up the number of demonstrating examples by multiple orders of magnitude to investigate the capability of the models to perform many-shot in-context learning, ICL. The performance is evaluated using standard metrics such as accuracy for multi-class classification datasets and macro-averaged F1 metric for multi-label classification datasets. Additionally, an ICL data efficiency metric is computed to measure the data efficiency of each model as the number of demonstrating examples is increased. The study also includes ablation studies to test the impact of batching queries on model performance and explains the substantial improvement observed in zero-shot settings. The results of the experiments are presented and analyzed to demonstrate the consistent and substantial performance improvements achieved by the models with many-shot ICL, as well as the impact of batching queries on performance, cost, and latency.
What results were achieved with this new method?
The new method of many-shot in-context learning, ICL, was evaluated on state-of-the-art multimodal foundation models, GPT-4o and Gemini 1.5 Pro, across 10 datasets spanning various vision domains and image classification tasks. The results showed consistent and substantial performance improvements, with increasing the number of demonstrating examples for both models. Gemini 1.5 Pro exhibited significant improvements on most datasets, with performance enhancements ranging from 16% to 38% compared to zero-shot or few-shot scenarios. Notably, Gemini 1.5 Pro continued to improve on 5 out of 10 datasets, even with the highest number of demonstrating examples considered. On the other hand, GPT-4o also showed substantial performance improvements on most datasets, although the improvement was not as consistent, with performance initially dropping before significantly improving as the number of demonstrating examples increased. Additionally, the study found that Gemini 1.5 Pro demonstrated higher ICL data efficiency than GPT-4o on most datasets, showcasing the effectiveness of many-shot ICL in enhancing model performance. The impact of batching queries was also explored, revealing minimal performance degradations, and sometimes even performance improvements as the number of queries included in each batch increased. Overall, the results demonstrated the effectiveness of many-shot ICL in improving model performance and reducing per-example latency and inference costs, highlighting the potential practical implications of this approach for adapting large multimodal models to new tasks and domains.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method include 1. The study only explores performance under many-shot in-context learning, ICL, on image classification tasks with private foundation models, limiting the generalizability of the findings to other tasks and upcoming open-source multimodal foundation models like LLaMA3. 2. The current context window sizes, even after recent developments to increase them, still prohibit many-shot ICL from being used on datasets with a large number of classes, which could restrict its applicability in scenarios with datasets containing several hundred or more classes. 3. The datasets used to train the private models have not been disclosed, making it challenging to determine if the models have been trained on the datasets selected for the study, potentially introducing uncertainties about the model's familiarity with the specific datasets used in the evaluation. 4. The study notes that zero-shot performance across the datasets is not perfect, indicating that the datasets may not have been used for training the models. However, this lack of transparency regarding the training data introduces a level of uncertainty regarding the model's training data and its potential impact on the study results. 5. Future work should explore how traditional fine-tuning of models compares to many-shot ICL with foundation models in terms of absolute performance and data efficiency, suggesting that further research is needed to fully understand the comparative advantages and limitations of these different approaches. 6. It is important to investigate general issues, such as hallucinations and biases in foundation models under the context of many-shot ICL and batching queries, indicating a need for additional research to address potential challenges related to model behavior and biases in the context of large demonstrating examples. 7. The study focuses on multimodal settings and image classification tasks, which are considered practically relevant and common, but the applicability and effectiveness of many-shot ICL on other types of tasks and datasets remain unexplored, highlighting a need for broader investigations into the method's performance across different domains and tasks.
What future work do the authors suggest?
The authors suggest several avenues for future work based on the limitations identified in the study. Firstly, they propose exploring the comparison between traditional fine-tuning of foundation models and many-shot in-context learning, ICL, in terms of absolute performance and data efficiency. This comparison would help understand the effectiveness of many-shot ICL in relation to the standard fine-tuning approach. Secondly, they highlight the importance of investigating how carefully curated and extensive sets of demonstrating examples can potentially mitigate issues such as hallucinations and biases in foundation models when utilizing many-shot ICL and batching queries. This exploration could provide insights into reducing biases across different subgroups within the models. Lastly, the authors suggest expanding the study beyond image classification tasks to explore the potential benefits of many-shot ICL in other tasks, and with upcoming open-source multimodal foundation models like LLaMA3. This extension would help in understanding the broader applicability and advantages of many-shot ICL in various multimodal settings.